Good morning, Year 11, and welcome back to your first science lesson of the half term. I hope you had a good break. First of all, let's have a look at the do now. If you haven't completed it yet, please pause the video and have a go. Okay, so hopefully we got the following. So the equation for kinetic energy is EK equals a half mv squared, mass times velocity squared. If you double the mass of the object and you keep velocity constant, then you're going to double the kinetic energy, because it's just a straight multiplication. If you increase that by a factor of 2, this increases by a factor of 2. So you double kinetic energy. The equation for gravitational potential energy is EP, potential energy, equals mass times gravity times change in height. Does a good conductor have a high or a low thermal conductivity? So it's quite obvious it's got a high thermal conductivity. It transfers energy easily. If you were looking at an insulator, that would have a low thermal conductivity. Bubble wrap contains air, which has a low thermal conductivity. So it contains air which has a low thermal conductivity. Okay, so let's have a look at today's lesson. We're going to be looking at the idea of efficiency, and we're going to look at the two different ways to calculate that. So if you can imagine any appliance, any device, you're going to put one form of energy into that machine or that appliance, and you're going to want to get a particular form of energy out of it. For example, a light bulb, you'll put in electrical energy and you'll want to get light energy out of it. Not all of the electrical energy will be converted into light energy. You'll also get some heat energy, and you might get a little bit of sound. So those two forms are called waste energy. That's not what we want. You'll have to be able to calculate the efficiency using the equation useful energy out over total energy in. And we'll go through this example here to show what we mean. We've got a solar powered aircraft here. It's got no pilot. That's not really relevant. But you've got light energy incident on these solar panels, and they convert light energy into electrical energy. So even though we're getting 175,000 joules worth of energy incident onto these solar panels, we're only transferring 35,000 joules of that into something useful. So it's not particularly efficient. This number is a lot smaller than that number. So let's have a go at the calculation. So as always, we're going to write the equation first. So efficiency is useful energy out over total energy in. That is 35,000 over 175,000. Pop that into the calculator. And that gives me a 0.2. And that's all we need to do. If you were asked to give it as a percentage, you could times this decimal by 100 and it would give you 20%. But the exam board now prefer you to leave it as a decimal. So this is the first way I've done it. We've used the energy to work out the efficiency. We can also do exactly the same if we know the power. So power is just energy per second, so it's almost an identical calculation. I've used the example of a leaf blower here. So he's blowing using the blower to move some leaves. It's powered by an electrical motor. The total power in is 750 watts. The output is 360 watts. I've just covered that over. That wasn't very clever, but never mind. So we've got 750 in. We're getting 360 useful out. So don't forget, a watt is 1 joule per second. So our efficiency equals power out over power in. That is 360 over 750. And that gives us 0.48. You'll notice I haven't put a unit on either of these. It's literally just 0.48. There's no percentage sign, there's no watts, there's no joules. Because you're dividing watts by watts, it cancels out, so it's 0.48. Again, you could multiply it by 100 to give you 48%, but you don't need to do that. You don't need to do that. You'll get the mark, but it's best to leave it like this. Okay, so you guys need to have a go now. You need to decide which equation you're going to use, obviously. So this one has watts, so we will use the power equation. You need to decide what goes on the top, what goes on the bottom, basically. Same again for this one, and same again for this one. The last question is a little bit more challenging. I'd like you to have a look through, and I'm going to give you a few hints, and then I want you to have a go yourself. So with this one, it's making it really, really tricky. So the first thing you have to do is calculate the kinetic energy. So your kinetic energy is going to be 0.5 mv squared. Once you've got that, you need to really realise that this kinetic energy is your total energy in. And down here, it's given us an efficiency as a percentage. I'm going to convert that to a decimal by dividing it by 100, and that will give me a 0.8 as my efficiency as a decimal. I'm then going to multiply that. So you start off with the equation, efficiency equals useful out over total in. We've calculated the total in, we know the efficiency, and now we need to rearrange to make useful out the subject. So you just multiply these two together. So your useful energy out is going to be your efficiency multiplied by your total energy in. We'll work out our kinetic energy up here, and then we can substitute it in down here. So our kinetic energy was 0.5 times 9,000. So hopefully we're well practiced at this by now. Times by 30 squared. That is 4,050,000. So 405,000. Yep, just double check that. That's good. So that's our energy in. Now we need to substitute into our equation the efficiency. I turned into a decimal, which was 0.8, and then the total energy in was 4,050,000. Chuck it into the calculator, and that gives me 3.24 million. So 3,240,000 joules. So tricky things to remember here. You need to convert your efficiency into a decimal by dividing by 100 if you get a percentage. It's always best if you have a decimal. Then you work out your total energy in, which was your kinetic energy, and then finally you rearrange the equation and substitute in. So quite a challenging question, but I'm sure you guys can manage it.